All right, so we are in Chapter 2, Section 8, looking at the last section, and it's the word problems. And now the word problems are probably the most relevant because that's what we do with all this math that we learn. We apply them. But they're also, they're the most challenging, to be honest with you. So make sure you take some time, try to let them grow on you. Hopefully you end up liking them. I wanted to look at a couple of them and get us going on how to set them up. So with number 3, they're talking about the radius r of a sphere is increasing at a rate of 3 inches per minute. So the radius r of a sphere is increasing. Well, we have a formula for the radius of a sphere, right? Or we know sphere, we get a volume equals 4/3 pi r cubed, and they'll go over some different formulas in the book, but I'm going to let my radius be x. So I get this formula. And so we see rates of change, right? As my rate of my radius changes, my x, my y changes. And so we can look at these relationships to see how, as one thing's changing, how the other thing is changing. And so doing these problems is basically manipulating some formula that we have that relates these two variables. Because once I derive my formulas, I can have a rate of change of volume over time. I can have a change of rate over time. And again, that's where that with respect to x previously is what we've been doing. Now it's within respect to time is what we're looking at. So I'm going to have supplements to the 2 word problems I'm doing, but we have to have that equation, the volume of a sphere, right? So the rate of change of the volume, here they are giving us the rate of change of the volume. They did not give me volume, they gave me the rate of change of the volume. Oh no, we're finding the rate of change of the volume when the radius is 7. So we know what dr dt is, the change in rate of my radius is 3 inches per minute, and then we're asked to find dv dt, an actual value, the rate of change of the volume when the radius is 7 inches. So I'll do a supplement for this one, but the main thing is we have to recall this equation. Another one I want to look at is number 5. So a 25-foot ladder is leaning against the house. The base of the ladder is pulled away, right? So they're pulling it this way, and it's at a constant rate of 2 feet per second this way. How fast is the top of the ladder moving? The top of the ladder moving when the base is given below. Well, if we are looking at this, I have this, I know this kind of looks like a triangle. Maybe like a Pythagorean, and x squared plus y squared equals hypotenuse squared. So we found this equation that relates our x and our y, our rate of change this way and our rate of change this way. So that would be the equation that we would start using, and then finding, I think we're looking for this rate, our dy dt. They've given us dx dt. It's a constant 2 feet per second. But my dy dt is going to change based off of how far I've pullen away from the house. So we will look at that one as well. So we're looking at number 3 and number 5. 3 and 5.